Okay. Hi, everybody. Today we're going to go over speeds and feeds in Fusion. Let me share my screen. Okay, here we are in Fusion. We're in the manufacturing workspace. Usually you launch into here in design, come over here, manufacture. So, setting up tools. We click, sorry, too fast. We come over here. We come up to tool library, hit that. Then we're going to come into documents. Right now, this document is untitled because that's what I've got up. But for you, if you're actually making a part, it should come up here with a name. Um, so you're going to hit the plus up here to add a new tool. Let's say that we're going to enter in a flat end mill. Beautiful. Let's say that we're entering in one that I bought from Amazon online. There's a company called Speed Tiger, which sells end mills. We're going to do a 1/2 inch end mill. So I'm just going to label it Speed Tiger 1/2 inch. For the cutter over here, this is our first page that we want to set up. Clockwise spindle rotation, always keep that. Keep all this. Number of flutes, we're going to pretend like this is an aluminum end mill. So we're going to go down to 3 flutes here. Change this to carbide. Honestly, it doesn't really matter, but it can help when you've got a lot of tools. Diameter. Couple things about Fusion. This FX here means that it is calculated from a different value. So you can see it's taking the value of tool diameter, which is up here. So when I change this to 1/2 inch or 0.5 and I click away, it updates down here to there. It's a shaft diameter. If you have a different shaft diameter, like 0.75, you can also enter that in. Generally, it's going to be 0.5, or it's going to be the same diameter. So overall length, you want to enter that in. Technically speaking, all this overall length stuff, this does not matter unless you're looking for clearance. So for flute length, that's the most important one. Move this up out of here. So this is this yellow portion here. And we're going to put the flute length at 1 inch. And you can see it's going to get angry at us. Shoulder length must be larger. It doesn't have a shoulder, so put it at 1.1. Doesn't matter. Length below holder. This one is important. This is how you're actually going to test clearance while you're simulating in your CAM software. So put this up, say you have 1.25 out of your holder. If you know that your clearance is fine, this does not matter at all. And don't worry about gauge length down there. Shaft, we don't care about. Holder, again, if you're looking for clearance, it's good to put a holder in here. I have a bunch from you can see their Haas tool holders up here. Generally, we're going to come down here to Cat 40 ER32, call it. That's a 2.5 inch gauge length. We're going to select that. We're going to do select holder. And now you can see, if I move my face out of the way, we've got a holder and we've got a tool in there. Nice. Okay, so we're going to come over here to cutting data. This is the most important part of your, does all your speeds and feeds here. So this is really important. So if you buy a Haas end mill, go over here to Haas tooling. We're going to go to, I don't even see it, mill tooling and end mills. And let's say that we bought, we're going to do inch, say that we bought a 1/2 inch Haas end mill. And we want to make sure that we have carbide selected. And we want to do a smooth shank, not a weld-in. Yeah, this 1/2 inch, 3 flute uncoated square is going to be perfect. 1 inch length of cut, which is already exactly what we entered in. So on Haas and on a lot of end mill sites, you're gonna have somewhere in the technical documents or specifications or something that's gonna say speeds and feeds. So, couple of things. I don't know where you guys are gonna be at when I'm making this video, so I'll go over it a little bit further. But side cutting, this is cutting with the side of the end mill. around a part. And HSM stands for high speed machining or high speed milling. It might also be called HEM, high efficiency milling, trochoidal milling. It could be a bunch of different things. So, but the important thing here is that when we're doing an HSM or HEM or whatever you want to call it, uh, when we use these speeds and feeds, we only want to use these speeds and feeds for high-speed machining. Excuse me. Okay, so we come down here and we have a bunch of different speeds and feeds. Right now, so I'm assuming aluminum 6061, which is an aluminum wrought alloy. And this is saying that it wants our width of cut to be at 0.05 times the diameter. So we're going to get to that. But what's most important right now is we're going to come over here. We're doing a 1/2-inch tool. We're going to come down here. It wants us to run 8,000 uh, 8,000 feet per minute on the surface speed. I think I'll explain. Well, this would actually be a good video to explain surface speed and that stuff. So surface speed is the actual difference in speed between your workpiece. Say that this is an end mill and your workpiece is this box. As your cutter is rotating around the box, there's a really small point of contact between the two. So how fast those rotate past each other is your surface speed. And that directly sets your RPM in the machine. So in this case, it's already done those calculations for us. So you can see the surface speed VC is at 8,000 and it wants our RPM to be at 61,100. That is not going to be possible in our machines. So for this kind of end mill, what we're going to want to do is just run it at the maximum RPM of our machine. So on the TM mills, that's going to be 4,000 RPMs. On the mini mill, that is going to be 10,000 RPMs. On some, it might be 12,000. Either way, we're going to run it at the max speed that we possibly can. So we have our RPM here in our surface speed. So we just know that we're going to be, in terms of the mini mill, we're going to be at 10,000. So we're going to come over here to Fusion and we're going to go into spindle speed and we're going to set this at 10,000. You can see that calculates 1308 feet per minute on the surface speed. That is vastly lower than the 8,000 feet per minute that Haas recommends, which is absolutely fine. When you lower your surface speed, you get a lot longer tool life and lower temperatures. So if your goal is to make tools last longer, then lower your surface speed. You can even lower it. Aluminum generally is pretty forgiving, but steel you're going to want like 200 feet per minute. Depending on your material. So now we've calculated that. Now we need to calculate the cutting feed rate. So as of this point, we have our RPM, so we know how fast this is spinning in relation, but how fast should it actually make a move along our part? That's what we're going for now. That's called your cutting feed rate. And your cutting feed rate is a product of your feed per tooth and your RPM. So you can see if it keeps these the same, if I run, say, 5,000 RPMs, you can see the feed per tooth changes to leave 40 inches per minute. Okay, so let's set this back up to 10,000. And we're going to go on here and it says VF. VF is going to be your cutting feed rate. The best thing to do is set it by surface speed and your inches per tooth. So this value and this value. These two get combined to make these two. In this case, I typed in an RPM only because we can't reach this RPM. If we could have reached it, I would have typed in the surface speed in Fusion. So in this case, inch per tooth, it wants us to take 14 thousandths on the inch per tooth. Wow, that is pretty high. Okay, 14 thou on the inch per tooth. So we're going to come back here. We're going to type in 0.014 for 14 thou per tooth. and that is going to run us at 420 inches a minute, which is incredibly fast. This is not going to leave a good surface finish. Again, this is only for high speed machining. So this would be a great roughing speed. So we'll so we've set that now, but now we need to make sure that we're only cutting, right? Where is it? 0.05 times our diameter. So we can go 0.0. So to set that, we're going to use a step over. So that's your width of cut is your step over. So we're going to do 0.5 inches, which is your end mill diameter, times 0.05, which is what it wants us to cut at, which means our step over is 25 thou. If you raise your step over, you're going to want to reduce your feed per tooth. Your spindle speed is going to stay the same, but these feed per tooth and therefore cutting feed rate are inversely related to step over. So we'll keep this as it is, and we're actually going to set our ramp feed rate up to 210, and our plunge feed rate, I'm going to leave at 100 because that is still extremely high for this small of an end mill. If you're doing a plunge move, I would highly consider looking further into this. So now that we've set that, generally I like to run the full flute because it wears evenly, so we're not going to change that. And we're going to rename this, and we're going to call it aluminum wrought because that's the alloy that we're cutting. And we're going to name it high speed machining, like that. We could also name it roughing. That would work as well. Then we're going to come down here and we just have side cutting here, so not high speed machining. High speed machining is called a bunch of different things. Like I mentioned earlier, high efficiency milling, high efficiency machining, bunch of different names for it. And what that is, I'll accept this for just a second. We're going to come back. You don't need to follow along with this, but when I go over here into 2D, we have lots of different toolpaths that we can choose from. When we do a 2D adaptive, so in Mastercam, they're called dynamic toolpaths. In Fusion, they're called adaptive toolpaths. And you can see here, it creates a roughing operation that uses a more optimized toolpath that avoids abrupt direction changes. So adaptive is high-speed machining or high-efficiency milling. So you only want to use that with this 2D adaptive clearing. But let's say that we want to clear something out, and then we want to do a finish pass around it, which is generally a good call. So that's going to be likely a 2D contour. If you were doing a hole or a bore, you would do a bore. Obviously, that's, if you don't have a drill, that's going to drill it. Stuff like that. So we're going to come back to our tool library. We're going to come back here to Untitled, and we're going to edit this tool. We're going to come over to Cutting Data, and we are going to duplicate this by doing add a preset. And we're going to call this one aluminum wrought finishing. So instead of high-speed machining, you could call this roughing. Only thing is that I like putting high-speed machining in here so that when you click it, it can only be used for one of these adaptive toolpaths. So when we duplicate this, you can see all the parameters are the exact same. We're going to come back over here. We're going to go, okay, side cutting. And this one is allowing us to take half the diameter. Now, I don't know if I'll talk about this in these videos. You never want to engage exactly 50% of your tool. So you either want to engage, 40% and lower or 60% and higher. And obviously, the more tool engagement you have, the less cutting feed rate you want to have. So in this case, just because we are doing a finishing pass, so let's cut 0.5 on the width of cut. I'm going to come over here. It's now doing 3,000 surface speed. Well, that is an RPM of 23,000, which we still can't hit. So we're going to leave it at 10,000. It is recommending an inch per tooth for finishing of 0.006. Now, this is something you're just going to have to to experiment with as you're running these end mills. So we're going to come over to here and we're going to do 0.006, and that's going to be a cutting feed rate of 180 inches per minute. Now, if you're really doing a finishing pass, I would say, so this toolpath or these feeds and speeds are going to work for anything that's not a high efficiency toolpath. In this case, I would run this down to maybe 2 thou per tooth and leave a nice surface finish. 60 inches per minute is not that fast, but you know, fast enough for finishing. And I don't think I talked about this when I was setting these ones, but your plunge feed and your ramp feed rate are generally going to be half of your cutting feed rate. So I'm going to come in here, enter 30, come in here, enter 30, and that looks good. Now for step over, I would reduce this down to 20 thou. I wouldn't be doing finishing passes that are over 20 thou. So if it says it's not really going to matter for contour toolpaths, yeah, there's some options in contour toolpaths which negate this. But it's just good practice so that you at least have an idea of what your step over should be. Okay, so that looks good for this. I set this up. So I'm gonna change this to a Haas half-inch end mill, and accept that. So now let's set one up as if we were doing, that Speed Tiger one. So we're gonna change this to Speed Tiger. We're gonna change our diameter to 0.5 inches, and we don't really care about this stuff for now. I just want to get across this cutting data part to you. So we have this end mill. We don't know where it's from. Say it's from AccuPro, which is MSC's end mill brand. They don't provide good speeds and feeds. So now we're going to go over a little bit of how to set them when we don't have this manufacturer's data. If you're buying an end mill from a reputable company, they'll always have this stuff for you, and it's generally good to run what they recommend. So we're going to come over here and we're going to go to Machining Advisor Pro. So this is an incredible app. You're going to need to create an account to use it, but it's free. It's no big deal. So Machining Advisor Pro is a subsidiary, or it's a tool made by Harvey Performance. So if we go to Harvey Tool Distributor, Harvey Tool, Harvey Tool is, same brand as all of these tools: Helical, Micro, Titan, Core Hog, Valor. So Valor's their drill. I don't know what Core Hog is. Helical is their normal sized end mills. So that's generally what you guys will be buying. Harvey does small end mills. So miniature end mills, material specific. Yeah, they do some weird stuff. So we're gonna go over here, click Helical, or you can just go to Helical. I just wanted to show you how they're related. So we're gonna go to products, right? So we have this half-inch end mill, 3 flutes, and we don't know where it's from. We don't know anything about it. So we just know it has 3 flutes and it's an aluminum end mill. So we're gonna go 3 flute aluminum and come over here. They have a bunch. This part can be kind of confusing. They have a bunch of options. Right off the bat, we know we're not a ball end mill, right? So we're not going to be this one. This, when it says corner radius, that's if it's a bowl nose end mill. So it has a little radius on the outside, so it's not square. We don't have a chip breaker. We're not coolant through, so we can, neglect all of that. So we're looking for a 3 flute, not corner radius. So down here, 3 flute, square, 35 helix, metric. We don't want metric. 3 flute, square, 35-degree helix. They also have these 40-degree helix. They are going to be remarkably similar. So let's click 3 flute, square, 35-degree. We're going to come over here. We know we have a half-inch end mill. So this is, I should explain a little bit. This is not, obviously we are not running this exact end mill. What we're doing is Machining Advisor Pro takes a tool number from all of those companies, all these Harvey Tool, Helical, all that. It takes those tool numbers and will spit out speeds and feeds for them. So what we want to do is find a really close match that helical tools will offer, um, but it's not actually going to be that one. So in this case, we said a 1-inch length of cut. I know I didn't set that in Fusion, but that's what we said for the Haas. So let's just stick with that. So 1/2 inch, 1-inch length of cut, 3 flutes, uncoated. If it is uniform in color, it's uncoated. If it has, kind of a yellowish color, a purplish color, there's a bunch of different coatings out there, and they're all going to look different. We're going to pick the uncoated one right here. So we're going to click this. We don't even have to click this necessarily. What we can do is copy this 01450. So I just copied that. Came over here to Machining Advisor Pro, and we're going to paste that in there. We're going to select this end mill once it pops up. And so we can see aluminum, 3 flute, square, 35-degree helix, 1/2 inch, length of cut 1 inch. So good, we've got the right one in there. So now we're going to set up our material. Our material is going to be, again, this is assuming 6061. They have a bunch of different materials that you can use. I don't know why it won't let me scroll, but there's definitely more if you can get in there. So aluminum alloy wrought. Oh, I know why it's not showing me anymore. If you have a 3 flute end mill, you can only really use that on aluminum, so it's only going to allow you to select non-ferrous alloys. So if I delete this, it only allows us to select, zinc, make all of these are non-ferrous. So aluminum alloy wrought. We're gonna come over here. It's a 6061, generally T6, and it's gonna spit out actually all these values at you, which is pretty cool. And you can even change. Say you don't exactly know what these values are. You can put this in and then just update these with whatever. If you have data on your material, you can just update it in there. So this is where we're gonna get into high efficiency milling again. So we're doing milling. And now we have a bunch of selections here. So full slotting is when it's cutting at 100% tool diameter, which is okay because we're not running it at 50%. 50% is the only bad number. So 100% is full slotting. So that's just creating a slot in the material. We're not going to be doing that. If that's what you need to do, then select it and go through it that way. But we're going to select high efficiency milling here. And that's our, optimized tool path that has rounded offsets with arcs. And that's the same thing as an adaptive tool path. So CV40 is a Cap 40 spindle. I think everything we'll be running at Cal Poly is going to be in a Cap 40 spindle. Yeah. So, and then holder, generally we're going to be in an ER collet. Sometimes you might have a weld in. If you're looking to get really good tolerance, go shrink fit, but we don't have any shrink fit holders. So ER collet, and it says, whoa, caution. Use this toolpath selection only if you're employing toolpath strategies with a high performance cam system that intelligent. Yeah, you get it. So this is just saying, make sure you're doing an adaptive toolpath with these speeds and feeds. Otherwise, you could break an end mill, by running a higher speed and feed or a higher feed because you don't, if you use it for the wrong toolpath. So we're gonna hit OK because we're fine with that. And immediately, without adjusting parameters, we're gonna skip a couple steps here, and we're just gonna go down to recommendations. It's recommending a speed of 24,000 RPMs, which is again faster than our machine can go. We're gonna come up here, enter in 10,000 RPMs, which is our machine max. This is a production calculator, right? So this is running production speeds on these. This Machine Advisor Pro and Helical and Harvey and all of them, all the tool manufacturers are going to make more money by recommending higher surface speeds because then you wear out your end mill faster and you need to buy a new one faster. In our case, we don't want to do that, right? We want to run these for as long as we can. So we're going to set all of our sliders down to 0, and I'll come back to that in a second. Work holding security all the way down. And you can see the feed per tooth down here change as I adjust this slider. So we're going to come all the way down there. And yeah, as long as you're not running production, you just keep it on the low end of this. So now it's spitting out feeds and speeds right here for us. And the value of most importance is really this MRR. That's material removal rate in inches cubed per minute. So that is actually how fast you're going to be able to remove the material from the part and how fast your part's going to be able to be made. Um, so down here, we, again, with these sliders, move myself off the side, we want to set speed all the way down. It doesn't matter because we're already maxed out at 10,000. And our feed all the way down. So that, again, is going to adjust our feed per tooth down there. Personally, I like running smaller radial depths. So in this case, I like running 10%. So we're going to do 50 thousandths, which is 10%. You can see radial depth of our tool. And axial depth, I generally just keep at full axial, at whatever the end mill is capable of doing so that I don't have to reset it if I'm doing a deeper cut than I need to. So now we've got, it's spitting out 8 thou per tooth at 10,000 RPMs. So we're going to come back to Fusion. We're going to do 10,000 RPMs. And again, if it wasn't 10,000 RPMs, I would be setting a surface speed. And our feed per tooth was, I think, 8 thou, not 80, 8 thou. That's 320 inches a minute. So you can see, already with those sliders we used, this is running 100 inches a minute less than that Haas end mill, which is going to give it better life overall. But we are also going to run, so we need to click this use step over, right? And we, if you can recall here, we used 50 thousandths on the step over. So we're going to change that to 50 thousandths. So this one, again, we're going to call it aluminum wrought high speed machining. And let's duplicate this, add preset, and we're going to name this aluminum wrought finishing. Even with the Haas end mills, so manufacturing data is great, or manufacturers' data is great, but they don't account generally for exactly the cutting or exactly what you're doing in terms of your depth of cut, your width of cut, what kind of tool path you're running, all that stuff. So that's where that Machining Advisor Pro comes in so handy. So we're going to come back to Machining Advisor Pro, and now we're not going to do high efficiency milling, right? Because we're just doing a contouring strategy or something like that. We're going to go to finishing. And it wants us to run a 20 thou finish pass, which is great. And it is recommending 1.8 thou per tooth. So we're going to come in here. We're going to change this to 1.8 thou per tooth.
You have Cody's roast?
I just saw him, but yeah, sorry.
I'll hop around.
All right, sounds good. Sorry for the interruption. So we're going to run this at 1.8 thou per tooth. And I just realized something. So when in Machining Advisor Pro, this spat out a feed per minute of 55 inches per minute. If I go here, this says 72 inches per minute. They should be the same. So I already know what's happened. I didn't make this a 3 flute end mill. So I'm going to go back here to cutter, number of flutes, 3, and carbide for good measure. Now you can see 54 inches a minute. That matches. That's good. We're going to do 27, if I can do math correctly, and 27. And this step over, it wanted a maximum of 20 thou. So we'll just do it like that. And we set this correctly too. Huh.
Quiet.
Oh, no worries. They can handle a little volume. Okay, so now that you've got that set up, I mean, at that point, it's pretty easy. You can go full slotting if you need to do that. Traditional roughing is going to be kind of like that side milling from the original one. Helical plunge is a good one if you're doing a bore toolpath. You can do a helical plunge. Trochoidal slotting, again, this is a high performance one. it's a slotting strategy, so it just does that full slot, but instead of, say you have a 0.5-inch slot, so you normally use a 0.5-inch end mill, we're gonna use a smaller end mill, like a 1/4 inch, and we're gonna rough it out like that. So you can see trick wheel slot width. Well, yeah, it's not gonna let us do a 1/2 inch one with this 1/2 inch tool, but um okay, so that's how you set end mill speeds and feeds generally. Face mill speeds and feeds can be a little bit testy. Maybe I'll make another video on that. Let's go set up a drill really quick and then I'll end this video. So accept that. We're gonna come in here. We're gonna set up a drill. We're gonna do a 0.25. Let's say we're doing a 1/4 inch drill. And we don't really care about this stuff as long as we've checked it, right? If you're not confident that you have the clearance, then don't negate this stuff. We're gonna come over to cutting data. Um, I won't go ahead here. We're gonna go, if I can get all this stuff out of the way. We're gonna go to carbide, depot, drill, speeds, and feeds. Carbide depot, high-speed steel twist drill, recommended speeds and feeds. Perfect. So we're gonna come down here, non-ferrous aluminum, 200 to 300 surface feet per minute. I'm gonna do 200 because drilling generally is not the longest part of your tool path. So 200 feet per minute there. And then you can see the feed rate is gonna be right here. So in this case, we're using a 1/4 inch tool. So we're gonna use 6 thou per revolution. So this is not 6 thousandths. This is not a plunge feed rate. This is a plunge feed per revolution. So we're going to change that to 6 thousandths. Perfect. And you're ready to go. Okay, so that should just about give you guys enough info to do speeds and feeds for end mills and drills, and maybe I'll do face mills another time. Generally what you can do is keep surface speeds similar. So, run a 1200 surface speed on your face mill at, maybe 5 thou per tooth. Your face mills generally can go up to like 15 thou per tooth and a bit higher, but yeah, okay. See you guys in the next one.